Hey guys, what's up everyone? Welcome back to my channel. Today we are going to talk about the direct comparison test. So the direct comparison test looks at two series, AN and BN. AN is the series that we're trying to find as to whether it's convergent or divergent. So we don't know if AN converges or diverges. We don't know. So this is our question mark. And so we are going to base it on BN then. We're going to compare the series AN with BN. So if we have BN being greater than or equal to AN, right? The terms inside of it, if this is true and say if BN converges, if this is true, then this tells us that this AN also converges. And that is if BN is greater than or equal to AN. Now, if we have BN being less than AN, and let's say BN, series BN, diverges, then that would mean that our series for AN also diverges. And this will allow us to determine whether AN converges or diverges. Also, a very important point I must note is that the series for AN and BN have to have positive terms in order for us to apply the direct comparison test. So say we have a series that looks something like this. Now we have to find a series to compare it to. So let's say this is our series. This series is like our AN in this case. And now we have to find a series BN to compare it to. So usually when we do this, we have to manipulate and play with the inequality symbols. So if we look at, let's say at the denominator, we have 11 to the exponent of n, right, plus n. So we take parts of this and we play with it. So we have this in the denominator. Now, we can say that we know that this is greater than 11 to the exponent of n because we're adding n, right? And n is just going to be positive numbers. So since this is greater, well, then we can look at the reciprocal of it because we're going to try and match it up with this AN, right? So we're going to try and match it up. So we're going to look at the reciprocal. And when we look at the reciprocal, we're going to flip. And since this is a greater number, this is going to be greater too. The denominator is going to be greater. And when the denominator is greater, it just means that this whole expression is just going to be less. So this whole thing is going to be less than 1 over 11 to the exponent of n. Now, since this is true, we can also try and match it up and multiply it by 2n on both sides because we're going to try to match it exactly as it is. So there we have it. And we can see that this is going to be our series for BN. So this is our BN, so we're going to write that this is our BN, right? This whole thing. And we can see that, hey, apparently our BN can be, if you see like these exponents of n, you can recognize it as a geometric series. So we can rewrite this as 2 over 11, close bracket, all to the exponent of n. And after this, we can see that, oh, well, we can rewrite this as a geometric series, and usually in a geometric series there's n minus 1, because if you look at a geometric series, if I was to write it, it would look something like this. It has a form with a, there's r here, and then n minus 1. This is all the way to infinity, n equals 1. So we're going to try to match up with n minus 1. So we're going to change this exponent. We're going to add 1 to it and subtract 1. So if you cancel it, it would be just n. So you can say that they're equal. And then we can manipulate it. And we can say that, we can just say, oh, well, 2 over 11 to the exponent of 1 is just going to be here, right? This is to the exponent of 1. And then we have 2 over 11 to the exponent of n minus 1. So this is going to be right here, right? This is just multiplied. If you were to multiply these two together, you would have to add the exponents just like we did here. So we're kind of undoing that part. And then what happens next is we can see apparently if we were to rewrite this without to the exponent of 1. So if we were to rewrite this without this right here, we can recognize this as our geometric series. This geometric series. So here we can see that our a is equal to 2 over 11 and our r is equal also to 2 over 11. And this is because this part is our a and this part is our r. And r is to the exponent of n minus 1, just like here, so it matches up exactly. So since we know this, and since we know that, oh, for geometric series, we know that, well, the absolute value of r, if it's less than 1, then it means that it would be convergent. The geometric series would be convergent. So here we have 2 over 11, and we know 2 over 11, the absolute value of this is going to be less than 1, so therefore, the series Bn in this case is convergent. And so we can say, basically, that this series converges. Now, we know that from before, that if we had Bn being greater than or equal to An, and we know that Bn converges, or we can just rewrite like this. If we know that this part converges, then An also converges. And since we proved that, well, this is our Bn, right? So Bn is greater than An, so we can even rewrite it. So here, this is our An, and this is our Bn. And our Bn is greater, see on this side, greater than our An. And since Bn is convergent, that will make our An, which is this series right here, convergent. So we can therefore conclude that this series converges by the direct comparison test. So now say we have a series that looks something like this. So this is going to be our An, just like before, because An is what we're trying to find. And we're trying to actually prove and also find whether the series is convergent or divergent. So if we look at, let's say, the numerator here, 2 plus En, let's just take parts of it and try to manipulate it so it matches with this, and also we get some sort of series to compare it to. We know this whole thing, right, is going to be greater than 1. It's going to be greater than 1, because if you were to plug in n equals 1 right here, if you were to plug in n equals 1, if n equals 1, then this is going to be equal to 2 plus e to the exponent of 1. And e to the exponent of 1 is like 2.7 something something, right? So it's going to be greater than 1, obviously. You're starting at 1. And if you're playing even bigger numbers, right, you know this is exponential and it keeps growing. It's just going to be bigger and bigger. So it's obviously greater than 1. Now, if we were to try and match it with this series, we're going to have to divide by 3n. So we're going to have to divide by 3n, and we have to do it on both sides. Now this is our an, okay? We can see our an apparently is greater than our bn. Now let's see as to whether this series converges or diverges. So this series, our bn, looks something like this. Our bn looks something like this, and we can see that we can bring up this 1/3 out of the summation symbol, just like this. And since we brought it right here, we can see, oh, well, this whole thing, what does this leave us with? It leaves us with a p series. And this is a p series with p equals to 1. So let me show you what I mean by that. The exponent here is 1. Our p is equal to 1. And there's a rule saying that if p is less than or equal to 1 in a p series, it means that this series will diverge. And this makes the whole thing diverge, basically. This is just like something being multiplied to it, a constant being multiplied to it. It's just going to make the whole thing diverge. So therefore, we can say that our bn in this case, because remember bn is represented by 1/3n, our bn in this case diverges, as this is our bn. This is our bn, so it diverges. And since our bn diverges, and according to the direct comparison test, if an is greater than bn, that means if bn is less than or equal to an, and let's say the smaller one diverges, then that basically makes this one, the bigger one, diverge as well. And so we can conclude that our an diverges, and our an, hey, is this given series, so this given series therefore diverges as well. So now let's say we have a series that looks something like this, along with some trigonometry here, you can see. So we have a sine function, right? So if we were to look at this, we know that sine, here it's 1 and here it's -1, right? The graph of y equals sine x, it's always between 1 and -1. You can see that. So it is apparent to us that this sine n can't exceed 1. It cannot exceed this 1. So if it cannot exceed this 1, this is telling us it has to be less than 1, and it can also be equal to 1, so you can include that. So that's what this sine n means. So now we're taking parts of this and trying to manipulate it so that we can find a series to compare it to. So now, since we know it's less than or equal to 1, we can also add 3 to both sides. So let's do that so we can make it very similar to our given one. And when we add 3 to both sides, this side becomes 4. And then when this side becomes 4, we can see, oh, well, we can divide by whatever is in the denominator. Let's do that. So let's divide by what's in our denominator. So we can match this whole thing up with this, right? You can see now it's the same. So once we do that, we can see, okay, well, this is going to be our an, right? This is going to be our bn. And also 4 divided by 2, oh, we can simplify that first before we even jump to that. So this is going to be 2 over en. And as we can see here, this is our an, which is what we're trying to find ultimately, right? And our bn is what we're comparing it to. Our bn is what we're comparing it to. And we can see that, oh, okay, well, let's look at our Bn. Let's see if it's convergent or divergent. So let's look at our series for Bn. Our series for Bn in this case looks something like this. Our series for Bn looks like this. Now we can see that this is a constant, so we could bring it out the front, so it looks something like that. And we can recognize this kind of looks like a geometric series. We're going to play with it and make it into a form of a geometric series. So we can just say this whole thing is to the exponent of n, because 1 to the exponent of n is just basically, well, it's just going to be 1, right? This is also 1 to the exponent of n, and we can basically, we can wrap the whole thing up like this, because 1 to the exponent of n is just going to be 1. It's not going to make a difference. So once we wrap this whole thing up like this, we can see that we can use the same trick we used before, where we add 1 and subtract 1 to the exponent. So we use the same trick. And then we're going to look at this and say, it's to the exponent of 1, right? So 1 over e to the exponent of 1, we're just going to write that out. So we're going to take this out. This is to the exponent of 1. And we're basically, according to exponent laws, you can see that this is n minus 1. So we're basically adding the exponents when we do this. So we're kind of like undoing that. And so we can recognize this as a geometric series. And this is because, well, it's going to be 1 over e, and this is 1 over e to the exponent of n minus 1. This is our a, this is our r, and n minus 1. Our geometric series looks something like this, with this form. And so our a is 1 over e, and our r is equal to 1 over e. And here in this case, we see that our r, well, we know the absolute value of r has to be less than 1 in order for the geometric series to converge. And here in this case, 1 over e is like 2.7 something something, right? So this is greater than 1, so it's going to make this whole thing less than 1. This makes our series Bn convergent because 1 over e, the absolute value of 1 over e is less than 1. And so according to the definition for a geometric series, it tells us that if the absolute value of r is less than 1, it makes that series converge. So it makes this whole series in all converge. And since Bn is greater than an, so since Bn is greater than an, and Bn converges, then that makes our an, converge as well. And this is because Bn is greater than or equal to an, and by a direct comparison test, since an is smaller, and an is what we're trying to find, and it's smaller, then it also converges as well. It follows the same behavior as Bn. So we're going to write that down. So this is our an, so therefore this series converges by the direct comparison test. Okay, so this is the end of the video. If you enjoyed the video and it helped, feel free to give it a big thumbs up. Also, let me know in the comments down below what you think about this video and what you think about the direct comparison test. Also, if you haven't already, feel free to subscribe if you enjoy my content. Well, anyways, I hope to see you next time. Have a nice day. Bye!